So far in this topic, we have been looking at acids and bases, particularly weak acids and weak bases, the salts of those and how to find the pH of them, and we've looked at titration curves. And in our titration curves, we identified a region called the buffer region, but I never told you really what a buffer was. So if I had a weak acid titrated with a strong base, then I tend to get a shape something like this. And we were saying that at the half equivalence point, so our half equivalence volume, the pH equaled the pKa of that weak acid. So the pH here was equal to our pKa, and we said this was the middle of the buffer region, the middle of the buffer zone. And the buffer zone was a pH plus or minus 1, so it's sort of about there. Well, what is actually happening in this zone? When I add, let's say it was ethanoic acid, because that's one we've used so much for our examples, with sodium hydroxide, then all of the sodium hydroxide is being used up in this reaction. But I haven't used up all of my ethanoic acid. There's still ethanoic acid in there, in this region here, before the equivalence point. There's still going to be ethanoic acid in there that hasn't reacted because I haven't added enough sodium hydroxide. It's not equivalent yet. So what I'm making is the ethanoate ion as sodium ethanoate, so I'm just going to write it a little bit incorrectly, like that, and water. So what I've got present in the solution, in this buffer zone, what I've got present is the weak acid, just didn't get my blue pen, and its conjugate base. Both of them are present in relatively equal concentrations. Because both are present in the same solution, even though I'm adding quite a bit of sodium hydroxide to it, the equilibrium between these two species can prevent a dramatic change in pH. It only changes a little bit, even though I'm adding a lot of hydroxide ions to it. And this is what a buffer does. A buffer, by definition, is a solution which contains a weak acid and its conjugate base in relatively similar volume concentrations, or conversely, a weak base like ammonia with its conjugate acid, ammonium, say ammonium chloride, for example. So a buffer is something where it has an acid, weak acid, and its conjugate base in relatively similar concentrations. What this means is that if I add a strong acid or add a strong base to it, the pH doesn't change much because the equilibrium is able to go either forwards or backwards to absorb that change using the Chatelier's principle. I'm going to show you what that looks like on an equation, because this is not the actual equation for the buffer. So the buffer is made up of both of these. So that what you'd expect is to put both of those as reagents and see what happens. It's not quite right. An equilibrium is saying that you've got things both on the reactant side and the product side. So what I'm actually going to do is write the equilibrium equation for this buffer. So the ethanoic acid ethanoate buffer, which is created in this zone here, is an equation you've all met before. It's actually just the dissociation of the acid. But now, I know that both of these are in roughly the same concentration. So at this point here, the half equivalence point, they're actually at exactly the same concentration. So let's call that concentration X. So if we assume that it's the half equivalence point, these two will be in exactly the same concentration. Exactly. All right? What we don't know is this one here. Now if we look it up, we find the Ka for this, and I'm sorry if I get this number wrong by the exact value, but it's something like 5.75 times 10 to the negative 3, something like that for the Ka. If I write my Ka expression, so there's Ka, It's going to be this times this, so X times hydronium. So I'm going to put Ka back in there, in case my number's wrong. That'll be living free wrongs video. Ka is going to be X times hydronium over X. Well, any number divided by itself equals 1. Ka equals hydronium. I'm going to do the P function to each of these, which is the negative log base 10 of each of them. So now pKa equals pH. That's exactly what we wrote there. Okay, so if these two are in exactly the same concentration, the pH of the buffer equals the pKa of the weak acid. So it's not a hard one to work out. Guess what? They'll never do that for you. So if you're going to make a buffer, they're going to give you slightly different concentrations of each of these. They won't be X. You'll have to plug them in and solve. However, I want to show you why these work. So I'll get rid of this. Because we don't need that proof, by the way. We're never asked to prove it. We've said it once in the last 10 years. If I was to add an acid, a strong acid, to this system here, this equilibrium, if I add a strong acid, that would increase the concentration of hydronium ions. Because both the acid and its conjugate are present, the equilibrium still has enough of the acid left over here to shift this way if it needs to make more of these products. But because there's a larger concentration of the conjugate, there's enough of this to also drive the equilibrium in the reverse direction to remove some of the stuff if they need to. So using Le Chatelier's principle, if I was to add a strong acid to this, it would increase the hydronium ion concentration. Le Chatelier's principle says the equilibrium will shift in a direction to minimize the effect of the change I make. So Le Chatelier's principle says that it will try to decrease the hydronium again. And that means it will favour the reverse reaction for a while. It will shift the equilibrium in the reverse direction until a new equilibrium is established where this goes back to where it should be, or very close to it. So the ratio of these things goes back so that the Ka is re-established. Right, so the equilibrium position is correct again. So this can only happen because there's quite a lot of the conjugate base. If that wasn't there, the equilibrium can't affect it. And that's why when you get to a certain point, the buffer is no longer effective. There's not enough of one of these two, so whoomph, we get the neutralization reaction finishing off. Likewise, if I was to add a base, this would decrease the concentration of hydronium ions, because that's what bases do, they neutralize hydronium ions. Okay? Or conversely, you could say they react with these to get rid of one of the reagents, because acid plus base is a reaction we expect to happen. Either way, it has the same effect. If I add a strong base, it will favour the forward reaction. This can only happen while there's enough of this for that to happen. So by having both the acid and its conjugate base there in similar concentrations, the equilibrium can shift forward or backwards to minimise the effect of the addition of a strong acid or a strong base. It only works to a point, because eventually it can't take it anymore and you get a sudden pH change. That's how buffers work. So I keep going back to this, both of them being present, that's what's required. A weak acid and its conjugate base are required for a buffer solution to exist. So that's our definition and composition. How they work, because both are present, the addition of a strong acid or a strong base only shifts this equilibrium, which actually maintains the hydronium ion concentration. It only changes a little bit, so your pH stays the same, pretty much.